Hello, everyone, and welcome. Good evening. I'm joining you live from Paris, France. Thank you for joining my virtual science camps for the fall launch. I'm excited to welcome you guys. I think we have people planning on joining from about 8 different countries. Um, hopefully, no one's having too many problems getting in. Um, Once again, welcome everyone. Bonsoir, guten Abend, marhabet, dzień dobry. Uh, Probably a couple other greetings that I've forgotten there. So the plan for this session, a lot of you are probably new to my virtual science camps. I recognize some familiar names who joined me in the springtime. But this evening, I'll take a couple minutes to explain what virtual science camps are, who I am, and why I'm running this. And then I'll run you through a couple of experiments, some highlights from the spring session, and a couple of things to expect in the coming weeks. So thanks again for joining and being a part of this. Give you a little bit of a background. Oh, actually, before we start that, in case you're new to Zoom or new to these camps with Zoom, just a heads up, you can switch between speaker view and gallery view at the top. When I'm speaking and showing you experiments, I recommend you'll probably get the most out of it if you have speaker view, so you see me nice and big. But you can change things into gallery view if you want to see other people who are sharing experiments. I encourage anyone who's brave enough when possible to share your camera so that we can see you doing the experiments and people don't think I'm just here doing it on my own. But I do appreciate some people might be shy. There might be technical difficulties. You might have a slow internet connection. So don't feel bad if you're not able to share your camera at any time. Also, please feel to speak up, ask me questions anytime you want. Verbally with your microphone is better. You can ask in the comments, but sometimes I'll be busy looking at experiments or my attention will be elsewhere. So I might be a little bit slow to pick up on things in the comments. So just keep that in mind. If I don't end up answering something you've asked, please either repeat the question or turn your microphone on and let me know, and then I'll be able to hear and answer it a little better. So yeah, I think that's all I had to say about Zoom for the moment. To explain what is a virtual science camp. So those of you who haven't joined me before, the idea is that I'll be showing you experiments that you can be following along at home with equipment you've gathered around. So I try and make the equipment suggestions very simple, like the €1 science. Coins will be the main thing for that. I'm impressed by how many people are joining me both from Turkey and from Iran. So your coins will be a little bit different. Looking online, I've been really confused about the coins that you're currently using in Iran. I think there've been a couple of currency changes. So maybe near the end of the session, you can help advise me on that so I can adapt materials for something you'll be able to find better. But anyone in France or in most of Europe should be able to get euro coins. I checked the Turkish, I think it's a 1 karash coin. I probably have the name of that wrong, but you do have a copper or predominantly copper coin that should work for some of the experiments we'll do. Some are completely independent of coin type. So that's the basic concept for virtual science camps, to get together and do experiments live together with things that come around the house. For those of you interested in who I am and how I got to be doing this, my name again is Michael Gregory. I'm coordinator of science programs for gifted kids at my school in Paris, France. But I'm of Canadian origin. You can see that from my t-shirt and the flag I'm proudly displaying behind me. And having lived in a bunch of different places around the world, I got to notice that even though science is universal and how it explains the world around us, how we teach it can be very different. So I decided to look up different ideas in different parts of the world. So far, I've been to 34 different countries asking teachers, educators, museum staff to share their favorite experiments with me. And I share that forwards both in my school and in further travels and in a YouTube channel I have, guest lessons I do in schools all around. And since March, in these virtual science camps. So I'm excited to have you joining me for that. Um, Probably it's most exciting if we get straight into a couple of the experiments. So one of the recommended materials I suggested you try and bring for this session is plastic drinking straws. I've got a couple
Okay.
right here. If you have them, can you hold them up so I can see them? Or if you're unable to turn your camera on, can you give
I'm
a
here.
excellent? We see that's Eli who has some, I think.
Gabriel.
Oh, Gabriel. Okay. Hard to tell twins apart sometimes.
Well, isn't it rated on my camera?
It is. I just wasn't paying attention that closely. And oh, and I was saying, if you're unable to turn your camera on, then can you give a reaction to let me know if you've gotten a straw by using the thumbs up in, like, if you don't know reactions, it's in a tab on the bottom. Reactions, you can give a thumbs up like I did right there, just so I can get an idea of how many people have drinking straws like this. Okay, and that's a handful, but that's far from everyone. So a good substitute material for this is a ballpoint pen. So you can use a pen for the same experiment. It just doesn't work quite as well. So it won't be quite as sensitive. Hopefully everyone has
one.
a pen. If you have straws, it'll work better. So use the straw. But if you just have a pen, you can use the pen as well. What we're going to do is take two of the straws. Oh, and this is a recap from one of the very first virtual science camps I did. I think the second one I did back in March. So again, the first 15 minutes or so, we're going to recap some of the highlights.
Oh, I remember.
So some people you may remember this, but hopefully it's still fun to try out again. So just take the straws and rub them in any material. I'm going to use my hair because you can see it. But you could use clothing, you could use paper, you could really anything you want. And did I tell you to grab a water bottle or did I forget that step?
I have one.
Okay, so placing it on the bottle cap, you should find when you bring one straw near the other, it'll repel. Same thing will work with pens, but pens have a significantly higher mass. And if they're similar dimensions, which they're roughly similar dimensions to a drinking straw, they'll be able to pick up a similar amount of charge because the acceleration is proportional to the charge and inversely proportional to the mass. The bigger mass of the pen will cause it to move a lot less. So you'll need to make sure you get it nice and charged for this to work. So we can see attraction of like charges, repulsion of like charges.
I think it works, I'm not sure. Well, I'm gonna try again.
Okay, and if anyone's having trouble getting it working, one of the things you can do is to make sure you're using the end that you charged. So
it works.
Here, I rubbed one end in my hair. If I try the other end, because plastic's a good insulator, we won't have any movement of charge and we won't get anything really happening there. So that was repulsion. We can show attraction. It's attracted to my hair, as awkward as that is. And that's because it's got a different charge. So electrons were transferred from my hair to the straw. We can use this principle to order a triboelectric series. So I'll go through a really quick triboelectric series before highlighting some of the other experiments we've seen. With any other materials you have around, doesn't matter which ones you have, which is why I didn't list other material, like I listed a couple other materials for other experiments. But for electrostatics, use your hair, use paper, use clothing. Like I've got a cotton shirt, I've got wool socks here. And I'm just gonna go through how we can order these and how strong or weak a pull they have on electrons. So first of all, we need to define which is positive and negative. And there's nothing that I could do with simple materials around the home to show which one is positive and which one is negative, other than convention. This was something that happened with scientists until the 1870s when Thomson invented the cathode ray tube, and they were able to shoot rays of electrons. Before that, there was no experiment that anyone was able to do in any lab to show which way was positive, which way was negative, or which way charge was moving.
Is it
As
simple electrification?
electrification, well, you can transfer charge between things, but the convention of calling one positive and negative is really just a convention until you can isolate a charged particle on its own, like an electron through a cathode ray tube. Does that make sense as an answer?
Yes, yes.
Okay, perfect. That was a great question. Thank you. Okay, so just a couple of different materials, how we would order this, and this is going to be like a lightning quick sample of going through it. So I'm always going to have my test charge from my hair, and I'm going to define the straw as being negative in that context. Now I'm going to take other materials. For example, I'm going to rub wool against paper. And I'm going to see if one is able to attract. So the paper clearly attracted. If the wool repels, which it does not, then we would have seen a clear separation of charge. Having both attract, that just shows there's no significant charge yet on these materials, because we'll get a false positive from induction. So I'm just going to try and rub that even more. Weaker attraction and very strong attraction. So it appears as if charge is going from the paper to the wool, and it's just going to need a lot more charging until I can actually get a repulsion from the paper.
No, I tried, and instead it's like a magnet. I tried with the paper, and it was like a magnet. Like when I was turning with the paper, and the straw was going like it was following the paper.
So that either means that it's got a different charge than the straw. So we said the straw is negative. That would mean the paper would be positive, or the paper might not have enough charge and it's acting like it's neutral and it's just attracting by induction.
Okay.
So that doesn't yet give enough information until you try whatever you charge the paper with. Does that make sense?
Yeah.
Okay, and I'm going to maybe give up on the paper and try a different material so that it should hopefully work. But I'm going to charge a straw against the sock. Okay, and we get repulsion there and attraction. So there, we know that the straw has a stronger pull on electrons than the sock. So we'll put it more negative in our triboelectric series. And I'm just going to order those on the desk in front of me. So all the way at the negative end is going to be the straw here. And if anything's more positive than it, I'll put it on this side, more negative over on this side. Okay, so I'm going to try now the paper against a straw. And that straw is also repelling. The paper is attracting, so the paper is more positive than the straw.
Oh, yeah, paper is more positive than straw.
And so far, we have a tie. We know that the straw is more negative than my hair, and that the paper and the wool have about the same pull on electrons. Just looking at the time, I'll stop it there. If you were to try another material, then if it gained electrons from the sock or paper but lost to the straw, it would go in the middle. Whereas if it lost electrons to everything, it would go to the other side, and so on. So it's kind of an incomplete run through, but just to have time to show a couple more experiments, I'm going to switch to another one. if anyone has a problem with that or has questions on that one and wants me to stick on that, I can try and answer more questions. I think the next one I want to show you, this will take the form of a tea break illusion. So I have a pot of tea that I've brewed in case I get thirsty while talking to you guys. So a pot of tea right in front of me. And because I'm in France, I'm going to use a wine glass because some people might think we drink everything out of wine glasses here. This is one I didn't ask you to do at home just because the materials are more time than it's worth for like a 2-minute demo. But I'm going to pour my tea into these 3 glasses. Oh, and it's herbal tea, so it's colored.
Is it hot?
It is hot. Like it's not great for the wine glasses that it's very hot. But like it's been sitting for a while. And if I swirl these around, hopefully it's showing up on the camera that we've got a little bit of a different color in each of these. This one's darker. Can you guys see that on the camera? Like if I hold a white background to it, it might show up a little bit better.
Oh, yeah.
But all the glasses appeared to be empty. So those of you who are along for my virtual camp on pH indicators might be able to guess what's going on here. And I had pre-rinsed 2 of the glasses, one with a base, one with an acid, and it turns out my tea here, it's a hibiscus cherry tea. And this is something I discovered just last week. I had left a glass of tea sitting out for a while, and I noticed it wasn't the same color it was before. And I started wondering why, and then I remembered that hibiscus is actually a pH indicator. So I'm going to grab the bottle of vinegar, and I'm going to grab some window cleaner, which contains ammonia, which is a base, and just demonstrate the color change more drastically. So we can see this one's like definitely a deeper, more purpley red, and this one's starting to lose some of the color. And it turns out almost any colored food, not every colored food, but like about half of the colored foods you could find will change color for a certain pH range. It's just most of the time these pH ranges are too acidic or too basic for us to really notice or care about, but sometimes they're relatively near to neutral. So that's a recap of the pH one. There's also, we've gone through making homemade pH paper. This is actually with cabbage juice. And it was cabbage juice we had impregnated, well, like soaked paper and then dried it. Kind of smells bad, but to demonstrate the effect of this one, I'm just gonna put some basic window cleaner. Getting it close enough to the camera, but hopefully close enough that you can see, but not too close that I'll get everything messy. And as we leave it to sit there, we see it's turning to a more green color, indicating a basic pH, a blue-green. And contrasting that to the vinegar. Put a little bit too much there, so it might be leaching the color out. But we can see definitely one is a lot more pink, indicating an acidic pH, and more blue. And that was something, those of you who joined me, some of you I think who were here today had been here for the pH one, where I was actually outside next to the Eiffel Tower because it was just after the last deconfinement. And so some of you might have a little bit of homemade pH paper left around as well. I think I have time to recap one or two more experiments from last time before going over some of the new ones to expect in the coming weeks. So let's look at one with surface tension. So I'm going to take this cup of water, and I think I asked you guys to have a cup of water and some plastic bottle caps handy today. So here's a cup of water, and I'm just going to take the cap off of my bottle of water and float the cap inside. And you'll notice, and this is more striking if you're doing it at home. So hopefully a number of you have a bottle cap and a cup that you can play around with. And if you leave it in the middle, it'll always float towards the side. I'll just move it a little bit closer. You can observe that phenomenon again. But my challenge for you is to figure out how you can get it so the bottle cap will float in the middle. Just by adding or removing water, adding the bottle cap. Can anyone either in the chat or with their microphone propose a solution to this? It's okay if you were around.
I think that maybe we can put not a lot of water, like not too much. I'm gonna see. Like so they will still have some water, but it will have less chance to go. Mom, can I have a cup? Is this a bit? No, not anymore. Wait, I'm gonna change camera.
And if anyone else thinks they have a solution, please jump in and feel free to add that as well.
Is it because that stick?
So it sticks to the side. It always goes and sticks to the side, and it's because.
Did you look on the email?
Ben oui. Il faut mettre Zoom.
Oh, it's not loaded.
And Gabriel, I'm just going to mute you for a sec while you try and figure out that solution. Does anyone else have a potential solution to this? If not, we can get back to that in a bit, and I'll kind of lead you towards a solution. So what I'm going to do is I'm going to fill this tray with a bunch of water. If your glass is big enough to fit 2 bottle caps, use a glass. If not, then like potentially grab a bowl or something, or just watch along. And here, now that it's full of water, well, I'll take the pH paper out, don't need that. And I'm going to put multiple bottle caps in here. And just observe what they do. And again, this is something that's even more remarkable if you're actually doing it yourself, because you might think, oh, maybe I have magnets hidden in my bottle caps or whatnot, but they'll always end up attracting each other, and they'll form islands. So once they get close enough to each other, and I'm going to try and separate this, and you can find it actually pulls some behind it.
Can I have like a tray?
Unless or until I pull it harder, and they'll spontaneously stick together. And the reason this is happening is because of adhesion. So adhesion means that water likes to stick to other materials. Water likes to stick to plastic, so it'll stick to the side of the bottle cap. And because it likes to stick to the side of the bottle cap, it'll climb up a little bit on the edge of it. It's hard to see, but if you look really close, you might notice it's got a little bit of a wetted edge. And because the bottle caps will float upwards, if they come in proximity with another bottle cap, they'll float up high enough, they'll actually rise up onto it. And that's what attracts them together. So if we pull them apart, we'll see the last maybe half centimeter or so is where they're the most attractive. And that's the same phenomenon happening in the water glass. but with the side of the glass, because water is rising up to the side of the glass. And the lowest point in the whole container is the meniscus, which is right in the bottom. Now we can do something to reverse the meniscus, and oh, does anyone have a solution from like all this lead-in, or should I go ahead and just show it to everyone?
Wait, I don't know why, but it doesn't really work. Look, if I change camera.
Which part doesn't work?
Well, here they're together, but when I move them, they don't go together.
Oh, they'll spontaneously. Sorry, they'll separate if you pull them apart hard enough. Like if you do pull them apart, well, it doesn't even take much force. You can like yank them apart and they'll come apart. But when they get close to each other, they should end up attracting the other one in.
Oh. So,
but it's not that they'll be stuck in any kind of permanent way. It's a fairly weak force, so it's easy to overcome. But in the absence of other forces, then it will cause them to stick together. So getting back to the cup of water, all I need to do is make it so that sticking to the side of the glass will actually make the surface lower, and we want the surface to be higher away from the edge. And the way we can do that is to fill the glass beyond full. So as long as I don't sink the cap in the process here, adding more water, eventually I get to the point where we have it full up to the rim. And I actually went a little beyond the rim already. I was hoping to leave it kind of at the rim point, but once we get it beyond the rim, the highest point will be in the middle of the glass, which is due to adhesion giving rise to the surface tension of water. And we saw that and played around with that in a little bit more detail in the camp on water and interesting properties of water. While I have everything wet, I'll do one last thing with water before getting to some of the things for the camps to expect in the following weeks. Okay, so the last demonstration of both surface tension and tying this into electrostatics. Again, if you can be doing this at home, it's much better than just watching. I'm going to take a couple of paper clips, and if I'm really careful with this, I can float the paper clip on the water. And paper clips, well, most paper clips, at least like these paper clips, they're made of steel, which is significantly more dense than water. But because of the surface tension of water, which is due to adhesion, water likes sticking to water. See, that's one I sunk. Water likes sticking to water. So unless we break that attraction of water, we can have the paper clip float on the surface. Now, if I try and bring the bottle cap near the paper clip, we see they repel each other. And they'll go away. But if we get two paper clips kind of near each other, just like the bottle caps, they'll attract.
Paper clip?
Yeah, just paper clips, like to stick papers together. And then to finish off this demo, I'm going to bring back in the straws that I charged electrostatically. So I'm going to charge those on my hair again. And we should. We can see attraction. That's because induction is always an attractive force. But when I bring it next to the paper clips, rather than attracting, it's actually pushing them away. And I'm going to get this bottle cap out of the way because the bottle cap will push them away as well.
Is it because electric charges?
Exactly, it's the electric charge on it, but we're used to seeing induction only attract things. So can anyone try and explain why in this case it could repel the paper clips?
2 1 of is negative.
So the straw is negative, but the paper clips are neutral. They have no charge on them. Just like the bottle cap has no charge on it, but it's attracted. And we'd usually expect a neutral thing only to be able to be attracted to a charged object. But here, the neutral paper clips are repelled by the charged straw, whether the straw's charge is positive or negative. So are there any hypotheses how that works? I'll give you a hint with a second straw that's not charged at all. When I put it in the water, it repels just like the bottle caps repel, the paper clips. And it turns out that we're able to attract the water itself. So if we attract the water that the paper clip is floating on, then that will raise up slightly higher by attraction to the charged straw. And because it's higher and the paper clip sinks slightly below the surface, it'll always sink towards the lowest point. And because it sinks towards the lowest point, then it'll move away from the straw. Are there questions on that before I move on?
And now what is the plastic role of its electric charge?
Sorry, I'm not sure I understood.
Just what's your YouTube channel?
Oh, my YouTube channel? It's My Favorite Experiments, like youtube.com/myfavoriteexperiments. In case anyone else is interested, I'll put a link in the chat. Okay, and that link should have gone through. If it didn't come through, let me know.
Where was it?
Just in the chat, which should pop up. Oh no, I sent it to the waiting room. Never mind. I'll send it to the actual meeting room. There, that should hopefully come through. Okay. For the upcoming experiments, so on Tuesday and the following Tuesday, and probably the Tuesday after that, although I haven't put that on a schedule yet, it'll be my new series called €1 Science, where we'll be doing experiments with money as the main thing. So the main thing we'll be using will be coins. We might occasionally use bills. One of the things that'll be really useful to know for people joining from places that don't use the euro is what kind of coins you have available so that I can adapt the experiments for them. So the one coming up on Tuesday, like a couple days from now, that'll be based mainly on simple chemical reactions with the copper of the coin. So if you don't have copper coins available, that one will be tricky to actually join in the experiment. You'd need to find other copper that you could use. So theoretically, any other inexpensive copper object. I think someone when signing up was saying in Iran you don't have copper coins. Can someone confirm or deny that so I know how much of a point this is?
We have got 30% copper.
Okay, perfect. So you do have copper coins.
Yes.
Okay, perfect. So, and 35 cents, you said?
Yes, 35%.
Oh, that it's 35% copper. Is the alloy such that it has a copper appearance on the outside, like these coins? Because for euro coins, The 22, well, the 10, 20, and 50, there's something called Nordic Gold, and these are actually 89% copper, but they also have 1% tin and 10% aluminum. And because of that, the alloy doesn't behave like pure copper at all. Whereas like a copper zinc alloy, which is common in a lot of countries, will behave quite similar to copper. Like for a number of years, both the Canadian and American pennies had that in their formulation. Now, Canadian and American pennies are like euro cents, like the 1 to 5 cent. And it's actually steel that's been plated with copper because steel is cheaper than copper.
Sorry, it's 90%.
90%. Okay, perfect. So that'll be that should be able to work quite well. So use that kind of coin for the experiment coming up on Tuesday, and we'll be looking at like basic scientific method, how we can look at different ways of cleaning it. Spoiler alert, one of the main ways we'll be using vinegar and salt, but we'll be looking at why that works and how can that apply in different contexts with different materials we might use to clean them. The one coming up next Saturday, looking at masks, I'm really excited about that one, just because a lot of people need to wear masks these days, so it's worth looking at a little bit of the science behind that. One of the things that we'll be using for that is water sensitive paper. I'll share a link in a couple days with how to make that. I'm still kind of finalizing my process for that because it's a new thing I put together for this, to be able to detect water droplets, to show that when you speak, then there will be small droplets of water that do come out just from regular speech, which is one of the bottom lines of why we wear masks. Then coming up the kitchen chemistry one, we'll be doing some basic stoichiometry, so balancing chemical equations, looking at reactional equilibrium as well, a temperature dependent reaction equilibrium. So that's kind of a preview of what's coming up. Yeah, just looking at time, it doesn't look like I have time to actually do like a hands-on part of any of those, but hopefully the suspense isn't too great and you guys are okay waiting for what's coming up. So looking at the time, it's 6:40, which is when I said I'd finish. If there's anyone who has questions that you'd like to stick around and discuss afterwards, I'm happy to stick around for as long as people have questions. But because it is the time I set, I'm gonna wrap up, and anyone who doesn't have anything they want to stick around to ask, this will be the end of the session. So I want to thank everyone for joining me and for your enthusiasm for joining in these virtual science camps. I've said it before in the spring session I was doing, but the key thing of it is having you guys along, following along with experiments, because otherwise I'm just someone sitting alone playing around with science on his own, and that's not nearly as much fun. So the real magic of this is having you guys join me. Thanks again for taking the time to join me, and I'm looking forward to seeing a lot of you back on Tuesday for the money laundering one. Thank you and have a great evening, everyone.
Thanks.
Thank you.
Thanks, Musa.
Thanks for the lesson.
Thank you, bro. Michael?
Yes.
Yeah, I didn't get why the you know, when the caps are in the water and you charge the straw, then you know, when the cap is neutral, you still get repulsion.
Oh, that's a great question. Thanks for asking that. So I skipped through a lot of that kind of quickly, just trying to fit a couple of different things in. But the best way to demonstrate that would be to go back to the straw. So I'm just going to charge a straw. And without charging a second object, so in this case, I'll just use my hand. It should be attracted to my hand. And that's because of induction. So induction will cause the charges within a material, like in this case, within my hand, it'll cause charges to move away. Like if the straw is negative, the negative charges in my hand will move away from the straw, just slightly, but it adds up to a big effect. And the positive charges will move slightly closer. Like they're within atoms, so it's not going to be a big movement. But that tiny movement will be enough so that it'll be an attractive force. And so anything that's neutral will be attracted to a positive or negative charge, as long as the charge is strong enough. Does that make sense in the context of the straw?
Yeah, sure.
So then if we go to the bottle caps floating in the water, it's the same thing. The straw is charged and the bottle cap's neutral, but it's going to cause a net movement of the electrons. Like if the straw is negative, the electrons will move away from the straw in the material, and not much because it's an insulator. But even just having the electrons on each atom slightly further over, added up over all of the atoms, that ends up being a significant charge. So it'll always end up being attracted. And that'll work the same if the straw was positive or negative.
If you use conductive, it will push it, isn't it? Or am I wrong?
That's an excellent question. And unfortunately, it's confused because I was using a paper clip, which is a conductor, and it was repelled, but it's because the paper clip is heavier than the water. Like we could demonstrate that if we had a paper clip, say, like floating on top of it. So if we float a paper clip in the bottle cap, and this will be like a kind of convoluted example. And just trying to get it so it can float like beyond the edge so we can see it even more pronounced, that it will be the paper clip affecting it more than the bottle cap. But now because it's floating above the surface, even though it's a conductor, it should be attracted. And because a conductor, we can have a net movement of the electrons, like they're not just going to shift within the atom, that they can move all the way from the other end of the paper clip. It would make sense if we get an even stronger attraction. I'm not sure if that's observable, if this is actually stronger, or if it's only about the same strength, but it would stand to reason that the paper clip being a conductor would have a stronger attraction to the charge, because we have it moving all the way along. So the reason why the paper clip was repelled is because it's sitting below the surface of the water. And it does that because it's heavier than the water. So unlike the bottle cap, that especially when it's full of air, it's less dense than the water, so it floats up higher. The paper clip is actually making like an indent, an impression into the surface of the water. Does that make sense, the distinction between, like, it doesn't, not that it doesn't matter at all that it's a conductor, but a conductor won't be repelled by induction. It'll still be attracted by induction, usually.
Okay.
That was a really good line of questioning. Does anyone else have any other questions they want to ask before we wrap up? Okay, so there are two questions. Bit more details about Tuesday's experiments. Okay, so the basic question will be, how can we clean coins? And so we're going to investigate with different materials you can find around the house. So I've suggested bring a couple of condiments like mustard, soy sauce, hot sauce, ketchup, 2 or 3 of whatever you easily find that you might have in your fridge. And it'll turn out most of the time, but there's some notable exceptions to this. Ones that contain vinegar and salt will tend to remove oxidized metals. But we'll look at how we can organize that or like make sense of those results. But then there's also some surprising things. Like if I had more time before we got to like whoever stayed after the end, I was going to show you guys some of these coins that I prepared ahead of time. And looking at these that have a green patina on them, which sometimes happens by accident, but it's interesting how you can get that reaction to happen intentionally and why you might want to do it in some cases. There's also some paper clips. It's not going to be completely clear to see in front of the camera. Sorry, relatively poor lighting. But I've actually plated copper onto the last 1.5 on this chain. So it's more of a copper color than the iron. So kind of introductory how we can plate metals onto things, which is an incidence or corollary of what we're doing to clean coins. So hopefully that explains a bit more what's going on Tuesday, and probably more detail I'll leave till on Tuesday. Then there's a couple other questions. One was, is this being filmed? And yeah, I'm filming most of the sessions to put parts of them on my YouTube channel for people who can't join in person. But anytime there's participants who appear, I'll either edit that out or I'll send you an email asking if I have permission to publish your image, because I don't want to publish anyone's image without their permission. I don't want to make anyone feel more awkward than they already might about sharing their camera. So that answers that question. When is the camp held on YouTube? I'm not sure exactly what that means. If that's like when will I put a recording of this session, in a couple days when I get around to it. And about ionizing the coins, well, there will be ionization within the solution, but it won't be like with electricity. I'm considering doing a session later on with electroplating and like electrochemistry, but I'm not yet confident that people will have enough simple materials around their home to do that. Like even if it's just with a battery, there's the question of, well, making your own wires or finding wires to connect batteries to the solution. And so might cover that in the future, but I'm not confident that that it'll be accessible enough for enough people. Okay, and probably because most of these questions are now about coins, and it'll be best to wait till we actually go through that in person. So I'm gonna hold off till next time to answer questions about coins, but I'm glad you guys are curious about it. Like the short answer, the green, because it's an oxide of copper, or in this case, probably copper chloride. And most copper salts are a greenish blue color. But like details on that, I'll go into that in a bit more detail on Tuesday. So I've run on fairly late answering questions. I'm going to wrap things up. If there's anything you urgently want to know or you want to talk to about privately, please send me an email and I'll be happy to hear from you. Thank you again for joining me, everyone, and have a great evening. Goodbye.